Yeah, is my screen visible?
Yes, sir. Yes, it's visible.
Okay, okay. And are you able to see the pointer?
Yeah, it's moving, sir. The cursor is moving. Point is.
Yeah, are you able to see a red line?
Yeah, red line is same.
Okay, okay. Okay, just let wait for another maybe 1 or 2 minutes. Maybe some more students will join.
Okay, sir. Okay.
Okay. Just let wait for 2 more minutes. Yeah, I am also visible.
Yeah, it's visible, sir. Visible.
Oh no, screen and my face is also visible or not? My face.
Yeah, in the top, both are slides and you also visible.
Yeah, okay, okay. Thank you, thank you. So this meeting is being recorded. Okay. So we will share this complete recording on a Google Drive, and we will also share the YouTube link of this recording on Google Drive. So from there you can see the video and all. We will also upload the PPT on Google Drive. So you can also access the PPT there. Okay, let's begin. So good evening, everyone. My name is Amit Kumar Sharma, and I am the course TA for course Energy Conservation and Waste Heat Recovery. The course instructors are Professor Prasant Kumar Das and Professor A. Bhattacharya from IIT Kharagpur. So I welcome you all to this first live session. So this is the live session for week 1. So I think as you have all already covered the week 1 classes taught by the professors. So now in this class, we will discuss some sample problems. Okay. So from the past week. So in week 1, you have covered the theory part, and maybe 1 or 2 numericals was also covered in the class. But in this live class, we will cover some more numericals so that you will understand that how to apply the concept to the numericals. Okay. And you will also learn that what are the how to solve the numerical. So that will be going to help you in your assignments. Okay. So I think you have your week 1 assignments, and I think you are having a due date to that assignment. So maybe I think this session will be very helpful to you. Okay, to know what type of questions are asked in the NPTEL assignments and all. Okay, so every week from 7 to 9, I will be here. Okay. I hope you will also join every time. So if you join regularly, so it will be very beneficial to you. Okay. And you can also ask queries. I will try to address all the queries. Okay. And meanwhile, you can suppose if the query is not able to we will not able to resolve in the live session, then you can also post on the discussion form. We can address it there also. So let us start with a little introduction. Okay. So I am a PhD student. I am in my PhD third year. Okay, I am at IIT Delhi, and currently I am at TU Delft, Netherlands, for my research work. So I am basically working on biogas powered solid oxide fuel cells for power production. And I am from basically mechanical engineering background. Okay. So let's start with the introduction of the class. Maybe one by one can just turn on their mic and you can introduce yourself. Okay, so like please also include like what is the motivation to join this course actually, yeah, because I want to know like what are you having in your mind that what will you get from this course. So it will be very helpful to me that so that I will try to cover those aspects as much as possible. Okay, let's start. Anyone?
So I'm Dr. Perisami, S. Perisami,
Okay,
Government
yeah,
College of Technology, Coimbatore.
yeah, nice.
I just know about this particular subject. I have mechanical background. I know about that energy conservation and waste heat recovery. That's why I'm enrolled. Till not a plan to go for a certification, etc.
Okay,
Okay,
so you are
thank you.
you are already teaching. Okay, you are teaching in BTech
I'm,
college.
I'm teaching, guiding. I have a research scholar, etc. But
Oh, nice.
now the most of the people are going to the energy conservation, etc. So they have to let you know some thing about that particular one. That's why I'm enrolled there.
Okay, okay, nice. Thank you.
Okay. Okay.
Next,
Hello, sir. Good evening.
good evening.
Yeah, this is Santosh Varan I'm from Bangalore. I'm a
Yeah,
postgraduate student. So I have done my post-graduation in thermal power engineering. Presently, I'm working in Tata Consulting Engineers, which is renowned for designing power plants and combined cycle power plants and all those things. So every day we deal with energy, we look into energy, we do the problems. So I want to just implement some of these techniques which are used here, and I want to upgrade my profile also, which will be useful for my career because I have started my career just now. So
yeah,
on a
nice.
short, this is my agenda.
Yeah, nice, nice.
Thank you.
Thank you. And actually, you can call me Amit. Actually, my name is Amit. So please don't call me sir and all because we are all like maybe some of you are professors and working professional. So it will be good that you can call me Amit. Yeah. Next.
Sure, sure. Thank you.
Thank you. Is anyone there? Next. Actually, I'm not able to see the complete list. Actually, I'm on in my presentation mode. Is anyone else? Okay. Okay. I think only two persons are there. Okay, no issues. We will start. So basically, this course, as you see the name, energy conservation and waste heat recovery. So this course is mainly focused on like waste heat recovery, okay, and how to conserve energy from that part. Because as you know, the waste heat recovery is a very important topic to cover. And like every industry, every process industry, they want to maximize their profit initially. So initially they don't go for the waste heat recovery. But today, as we can see that every government, every country's government, like okay, so they are focusing on climate issues. Okay, so they are implementing some restrictions on the companies or industries that they have to uh, follow some standards. Okay, so so those standards also include like they have to minimize the waste heat, or they have to maximize the efficiency. Okay, so that and they have also controlled the pollutions emission from their process. So in those fields, so the waste heat recovery plays a very important role because if you are recovering the heat from the waste heat, okay, Like if you are having high heating source and your exhaust is very high temperature. So if you are recovering heat from that source, so it means that you are reducing the emission, you are reducing the fuel input. Okay, your efficiency is going to be high. So in this case, there is a win-win situation. So it's a very, very good topic to cover, and it's also have a huge practical application. So in this course, first we will start from the fundamentals, like what are the fundamentals of thermodynamics. Okay, we will start with very basic, very basic simple problems. Maybe these problems you already knew, but maybe it will be good to brush up your concepts. So we will start with very basic problems, okay? And slowly by week, we will go deeper in the subject and you will get to know that what are the technologies that are going to be used and what are the fundamentals behind these technologies. But remember one thing, it's going to be very interesting in this course and it will be very useful to everyone. So those who are here and those who will be going to watch this session live later, so it will be it will be going to very useful all of you. So let's start with some basics questions. So the first question is, so in this session we will try to solve the question, and through the questions we will discuss some concepts. Okay, this is going to be the strategy for these sessions. So in this, like there is a one question. So I will give you 2 minutes. Maybe in 2 minutes, please try to solve the question and tell me the answer. So then we will discuss it. So we will discuss it. Okay. So the question is, which of the following strategies are most suitable for waste heat recovery in a plant with an unavoidable generation of waste heat? So we have to identify the strategies which are very useful. So these are, first one is adoption of waste heat recovery principles at design stage of the plant, retrofitting waste heat recovery technique in an existing plant, and redesigning the existing plant to implement waste heat recovery principle. So go thoroughly through all three options. Try to remember the class notes and try and answer me. And please also remember one thing, in NPTEL, it is not necessary that only one option is correct. Okay. So more than one option can also correct. So in every question, think through all options. Okay. Don't directly strike that. Suppose you see that only option A is correct. So directly you can say A, but maybe option B is also correct. So go through the all options, understand the question thoroughly, then answer thoroughly. Okay. Just have 2 minutes and share your answer and we will discuss it. Yeah. Am I audible?
Yes, yes.
Yeah.
Yes, sir.
Thank you. Yeah, if you face any issue like in my audio or in my video, please tell me. So do you have any thoughts about this question? Anyone? What should be the answer?
One and two only.
Okay, 1 and 2. So one is the adoption of waste heat recovery principle at the design stage, and the second is retrofitting waste heat recovery technique in existing plant. Why 3 is wrong in your opinion? What is the reason for first to be wrong?
Third also you can include, but as for the designing aspect, the redesigning of the existing plant sometimes is very difficult, or it will be major redesign.
Yeah,
is to be
correct.
happened.
Yeah, actually,
That's why
suppose
first two I prefer.
Yeah, nice. So yeah, correct options are 1 and 2. Okay, because adoption of WHR principle at design stage of the plant, so it will be very easy. And when we are designing the plant, so that the all systems are new, all designs are like in draft stage, so we can discuss it, we can change it, and we can like we can have an optimized design. So the design stage is the best option. Second, retrofitting WHR technique in an existing plant. Suppose we are having an existing plant. Now we think we can use the waste heat recovery. Okay, because in market there is a new technology that is a very good. So we can install that technology. So we can retrofit that. Okay, so we don't change the design. The plant is same. We are just installing a new system for waste heat recovery. That is also good. The third option, redesigning the existing plant to implement WHR principle. Yeah, it's going to be very difficult. Redesigning it, as it the option is like saying the redesigning the existing plant. So you cannot redesign because you know that when we are installing a plant, so it's having a huge cost. Okay, so it's very difficult to redesign. We cannot redesign any plant. Okay, so whenever a plant is installed, it is for maybe 20 years, 25 years, 30 years. So redesigning it not possible option. So option third is wrong. So the correct options will be 1 and 2. So now check the options in A, 1, 2, and 3 all there because 3 is wrong. So option A is wrong. B, 1 and 2. Yeah, B is correct. C, 1 and third. Third is wrong. So option C is incorrect. D, second and third. Because third is there. So option D is also incorrect. So the correct option will be only B. Okay. Is there any doubt? Okay. Let's come to the question number 2. Question number 2 is utilizing waste heat recovery one can generate. So suppose you are having a plant and you are utilizing the waste heat recovery. So what are the possible options you have? So you can generate like either option 1 electric power directly, option 2 electric power indirectly, option 3 mechanical power, option 4 heating, option 5 cooling. So take 2 minutes, go through all options, think about these options and answer. So any thoughts? Anyone?
So option A.
Option A, 1, 2, and 3. Okay.
C.
Option C, 1, 2, 4, and 5. Okay. So let's first go with option A. So what are the reasoning behind option 4 and 5 to be wrong?
Actually, sir, in my opinion, it should be 1, 2, 3, and 4. But
Okay.
since there is no option available, including all those 4 options, that's why majority of options were in A, so I have chosen A.
Okay. So you think option 1, 2, 3, 4 is correct, only option 5 is wrong. You are thinking that.
Yes, sir.
Yeah. Okay. So why the option 5 is wrong? Why do you think so?
Sir, because I think if we are recovering the waste heat,
Mm-hmm.
so can't be utilized in cooling, because in cooling we have to use a sort of coolant.
Okay.
And so since we are using heat to generate, we can use heat to drive the turbine, so mechanical power, and we can drive the turbine to the electric generator so that electrical power is also generated, and we can use the waste heat to direct it again for heating purposes.
Yeah, right. Okay, so correct. So we will come to the cooling part. Okay, but your other options seems to be correct. Okay, we will come to cooling also. Any other over also? No, you were telling option C. Your name, please.
Anyway, so all the things are possible. So I think it's D, and the
Yeah.
part is D. Directly you can use for heating purpose also. Suppose
Okay.
you have any of the Seebeck and the Peltier type of effect, you can get a cooling also.
Yeah. Please explain about cooling. How we
Yeah.
will get cooling from waste heat recovery?
So the
It's like vapor absorption system, refrigeration, one of the system where waste heat is used.
Yeah, right.
Vapor
Right.
absorption cycle,
Yeah.
where we can do the cooling there.
sometimes some
Yeah.
people are doing the Peltier and Seebeck effect alternatively. The one side, if you're giving a heating using the electronic in the piezo in the Peltier or the other type of Seebeck effect, you can use that other side as a cooling purpose.
Cooling purpose, right, right. So yeah.
Otherwise, in the pre-stage system, the refrigeration type of somebody told that type also. The hope.
Yeah, correct. It's a great discussion. Yeah. So yeah, all options are correct. Okay. So we can also do cooling. Okay, heating, cooling, mechanical power, electric power directly and indirectly. So the correct options will be D. So waste heat can be generate anything like electric power directly, indirectly, mechanical power, heating and cooling. It depends on technology. Okay, which technology we are going to use. So the
Excuse
correct
me,
option will be yeah.
sir. Can you give some basic examples of for all the options? It's like just to have a more understanding.
Yeah, actually, we will come in our like next weeks. So we will cover all technologies, but like some examples I can give you. Like if we are having waste heat, okay, so we can use that heat to generate steam, okay, and we can from that steam we can run steam turbine, we can generate electricity, okay. We are having some like with thermoelectric devices are also there. I don't know exact name. So they are using heat and they are having some reaction that they can generate electricity. Like mechanical power, again you are generating steam. So maybe with the steam you can guide that steam to turbines and you can run the motor. So mechanical power is
Or
also there.
an automobile, something kind of automobile.
In sorry, in automobile what?
It's like mechanical power. We are using the steam and we can run an automobile with it.
No, that is going to be quite difficult because in automobile is not a stationary system and waste heat recovery. Yeah. So normally, if you go for waste heat recovery, so one thing is to be you understand that it's depend on the quantity and quality. Okay, if you are having waste heat, it is not. It doesn't mean that always you can extract it. Extract it. Okay. It also depend if the waste heat is in good quality and good quantity, then only it's going to be useful. Like for automobile, if we are discussing that, then automobile will be having a very low waste heat, so that doesn't recover easily. And if you want to recover that, that going to be very costly. So that not to be economic feasible. So normally we employ waste heat recovery systems on large stationary plant like some oil industries, some big process industries on those plants, because there they are having big systems, big boilers, big machineries. So they are having huge high temperature exhaust. Okay, they are having huge heat exchangers and all. So there we are having huge opportunity to tap off the waste heat. So we have to understand it. Okay. Quality meaning, I am saying the waste heat quality means like temperature. If suppose you are having waste heat at 100 degree, and other side you are having waste heat at 500 degree. Okay. So that 500 degree is going to be more useful than 100 degree, because if you are having a 500 degree temperature, means you are having more energy to that, and you can do like multiple use for that heat, because you are having huge temperature difference, so you can do multiple things. But on the other side, 100 degree, it's not very useful. Okay, because we know that when we try to convert, heat is low grade energy. Okay, it's not high grade energy. So whenever you will convert it, so there will be further efficiencies will be applied to this. So the net output will be very less. So if you are 500 degree, maybe net output will come around 200 degree or 100 degree centigrade. But if you are having only 100 degree centigrade, it's going to be very less. So it depends on the quality and quantity also, like what is the mass flow rate of the waste stream. Okay, because quality and quantity both are important. So based on those, based on your like plant, your quality and quantity, we have to select the best technology to recover the heat. Okay, it's actually uh, a very tedious job to select the correct options for waste heat recovery. It like not random, like we can directly select mechanical power, electric power. We have to check all the parameters, all the options, then only we go for the option. But these are the things uh, uh, that can be possible from waste heat recovery. But in practical application, we have to check various parameters. Okay, I think your doubt is, I have cleared your doubt. Anything
Yes.
else?
Thank you.
Yeah. So let's come to the next question. So the answer is D. Question number 3. So which one of the following is oblique are the reasons for waste heat generation? Option A, thermodynamic limitation of cycles. Option B, heat transfer limitation. Option C, or you can say 3, physical limitation of the equipment. 4, characteristics and chemical composition of exhaust streams and plant layout. Go through all the options and come with a solution.
Excuse me, sir.
Yeah.
Sir, can you please move the pointer because I am not able to see the B option. Thank you, sir.
Okay. Okay. So do you have any answers?
It's
B,
option C,
sir.
sir.
Option D.
C.
Option C. Okay. So you are saying that option 1, 2, 3, and 4 are correct. 5 is wrong. Okay. So just discuss your reasoning for option 5, plant layout.
I'm sorry, I think it's option D. Fifth option also should
Option
be
D. Okay.
the option also should be there.
Okay. So what is your reasoning behind option number, like first option, thermodynamic limitation? What do you mean by thermodynamic limitation?
It's like if you want to satisfy the second law of, you have to somehow release the heat, the excess heat or something. The some amount of heat has to be released. So that is the reasoning for it.
Yeah, correct.
So,
Anyone else want to add any point to this? Actually, if we discuss more, then maybe it will be very beneficial to all of us, because because in discussion, various points will come and we will get to know various aspects of thinking. Yeah, it's going to be very great actually. Yeah. So anyone want to add any points to the option 1, thermodynamic limitation of cycles? What do you think about this option? Why this is correct? So I think one is said that we are governed with thermodynamics laws. So this is the point coming in this option. Anyone else want to add any point?
Hello, sir. Good evening.
Yeah, good evening.
For example, in case of Rankine cycle, if you just, because of the cycle, we cannot go beyond certain pressure limit at the exhaust. So for
Yeah.
that case, yes. So for that case, because if you reduce the pressure to just extract more amount of work, still there will be other difficulties. So for that case, this thermodynamic limitation of cycle is one of the answers.
Yeah, correct.
And
So,
as the pressure, so temperature will also reduce. So the heat, whatever the energy which is going to be coming out, will be reduced. But on the other hand, it will be having some more difficulties with the cycle, in the cycle.
yeah, right. So basically, more or less, we are governed by thermodynamics laws, and thermodynamic laws are say that nothing can be 100%. Okay, so there will be always some limitation, thermodynamic limitation of cycles. Option 1 is correct. Let's come to the option 2, heat transfer limitation. So what are your thoughts? Please share.
so it's like reversible process and such kind of things. Why? Because you cannot transfer entire heat, something like that.
Okay, do you think like normally, suppose if you want to transfer heat from a hot stream to a cold stream, then what kind of technology we do use in our normal applications or in
Heat
industry?
exchangers.
Yeah, so we use heat exchangers. So is there any limitation in heat exchangers?
So it's like that will come under the physical limitations of equipment. Why? Because you cannot have infinite length of equipment or larger surface areas or something like that. So
Yeah.
to achieve that, something like that. So physical limitations of the equipment will come into picture at that point.
Yeah, physical limitation will come into the heat exchangers if we going with the you can say that like we are discussing about the equipment then. Okay, but normally suppose there is a hot stream and there is a cold stream. So there will be limitation of heat transfer.
Good evening, sir.
Yeah.
Sir, as per thermodynamics law, it is said that there can be no machine designed or no engine designed that sole purpose is to transfer heat into work.
Yeah, correct.
So I guess this is one of the limitations for heat transfer, that we cannot design any engine or any pump or any sort of machine that can transfer whole heat into 100% work.
Yeah, that is okay. But yes, suppose we are not transferring heat to the work, that you are saying correct. But think about like suppose we have to transfer heat. One is hot stream, one is cold stream. Okay, and we have to transfer the heat. So what will be the heat transfer limitations? So one is physical limitation. Suppose the equipment which we are using. So that will come under the physical limitation. Like suppose we are using some equipment, okay, that equipment is not able to transfer the complete heat. So is it only due to the equipment that we are not able to transfer the complete heat, or still there are some other limitation due to which we are not able to transfer the complete heat? Just think about that aspect. So if we are discussing about equipment, then one thing one person said correct. Yeah, we are having physical limitation of the equipment. Let's suppose if we are having parallel flow heat exchanger. So this one is suppose your cold stream, sorry, hot stream. This one is your cold stream. So here you can say the temperature is decreasing and here temperature is increasing. So there will be always a temperature difference between the endpoints. Okay, so maybe at the end point it will come mostly you can say at a break even, but that will not possible. It will be going to be at infinite distance, so that but infinite length of heat exchanger is not possible. So there is a physical limitation. But what is the heat transfer limitation? So that is, suppose we are transferring heat. So what is heat? Is low grade energy or high grade energy?
Low grade energy.
Yeah, heat is low grade energy, and we have also discussed about the entropy generation. Okay, so whenever like we will transfer heat, so we are going through some process, maybe, because if you are transferring heat, so you are doing a process, a thing. So there will be more and more like you can say various changes will be going to happen. So they will increase the entropy of that particular process, or maybe in that way we can think, so that some part of heat will be lost. So there will be heat transfer limitation due to again thermodynamic principles.
So you can
Maybe
say
some
that it's
other
considered to reversible and irreversible processes, where in irreversibility more entropy generation, more
yeah
desired results will come.
yeah, irreversibility, correct word, irreversibility. Yeah.
Yeah.
So we can consider it like irreversible cycles. Yeah, because every cycle is theoretically irreversible. Okay,
Irreversible.
because yeah, when we are going through, so there will be microscopic changes, macroscopic changes will be there. So they will increase the entropy. So the complete heat will not transferred. Okay, so there will be limitation. Third one, physical limitation, as we already discussed, that because the equipment is also have some limitation, some efficiency. Maybe the material of the equipment. Okay, because we are using some tubes. Tubes is having some material. They are having their conductivity, their coefficients of thermal coefficients and all. So there will be physical limitation. Okay,
Thermal
the fourth one is
resistances.
fourth one is characteristics and chemical composition of exhaust stream. What about this?
Sir,
Yeah.
sir, I want to add something in heat transfer limitation.
Yeah, please.
Like in case of any heat exchanger, like what type of fluid we are using to extract the heat energy, that will add one limitation, and that will be like that will be able to only extract certain amount of heat energy at a certain temperature. So that might be one point in case of heat transfer limitation. Apart
Yeah,
from
correct.
irreversible thing, and moreover, like physical limitation, like we know that how much amount of heat we are going to be giving out at the exhaust. So accordingly, we are going to design our heat exchanger to extract that heat.
Yeah, that is also correct. That is also correct. Yeah. Now come to the fourth point. Characteristics and chemical composition of exhaust stream. Why this is important? Chemical composition and characteristics of exhaust stream.
So in the exhaust stream also some heat will be generated. Suppose the unburned hydrocarbon or even the carbon monoxide that will be gets in that oxygen in the atmosphere contact, in the sense that will be making a combustion that will be generated heat also. or while moving through that one, even the boiler, so many places it may have an exhaust stream alone. The process may be happening, the combustion also happening depending upon the fuel availability.
Yeah, correct. So chemical composition of exhaust stream can also be a reason of waste heat generation. Fifth is plant layout. So what should we consider in plant layout? So option C is correct, like 1, 2, 3, and 4, or option like plant layout is also correct. What do you think?
So plant layout is also correct, sir. I think so. In some of the plant systems where there is a source of heat energy, and you cannot transfer that heat energy to other streams due to the space availability and all those things. So at that point, you have to lose that heat there. So if you are not
Yeah,
using that waste heat recovery principles means, so that in
yeah,
that way we can say.
correct. Because plant layout is having a huge factor in waste heat generation. Okay, because whenever a company is installing a plant, okay, so they don't optimize everything. So plant layout is having a major reason. These are the limitation, like thermal limitation we cannot control. Okay, physical limitation also depend on the equipment. These are like always will be there. You can like just you can reduce maybe by optimizing the your cycle and optimizing the equipment. But the plant layout is main thing. Okay, because like one said, we are having space constraint. Okay, we are having ventilation constraint. We are having various type of constraint in the location itself. Okay, so based on that, anyone want to design the plant? So maybe their design is not efficient. Okay, so that will be going to be a main reason in the reason of waste heat generation. So that plant layout will also be going to be an important point. So the correct option will be D. 1, 2, 3, 4, and 5. So all options are correct, and all options are the reason for waste heat generation. Okay. Okay. Let's come to the next question. So question number 4 is, which of the following are sources of waste heat? So earlier we have discussed the reason. Now what are the sources of waste heat? The first one is fossil fuel based power plant. Second is hydropower plant. Third, nuclear power plant. Fourth is hot products in metallurgical process and chemical industries. Go through all the options. Think about it.
So C
Anyone?
option.
Option C. First, second, and fourth. So fossil fuel based. Okay, so what is the reasoning behind fossil fuel based power plant?
So since fossil fuel based power plant, we can take the example of a thermal power plant in which coal is used.
Correct.
So sir, that coal, when we burn the coal, some of the percentage of heat is wasted
Okay.
and it is not recoverable.
Correct.
The reasoning behind option 3, that is nuclear power plant, is when there is nuclear fission,
Mm-hmm.
a large amount of heat is released, but the same reason, the 100% of heat is not being used to convert steam.
Yeah, correct.
And sir, I guess same reasoning applies in the fourth option also, hot products in metallurgical and chemical industries. Sir.
Okay, so what is the reasoning behind option second? Why it is wrong?
So because in hydro power plant we use solely gravitational energy of the earth, that from a high ground we open the dam's door and the water flows to the turbine and electric generator produces electricity. So here sir, no heat is being evolved or generated, so I guess there is no waste heat over here.
Okay. Anyone else? Yeah, thank you. Thank you for your good points. Anyone else want to add something to these points?
Can we say that for hydropower plant we use renewable source of energy?
But the question is asking about the source of waste heat. It's not mentioned that maybe renewable energy source can also generate waste heat. It's not that the renewable source. It's about waste heat. You have to think in that perspective.
Then we can say that there is no any thermal energy being involved in hydropower plant, as one of our friends said that.
Yeah, that is actually I want to hear, because normally you can see that in every first, third, and fourth there is thermal energy involved. Okay, there is either combustion from thermal energy is there. Okay, so and we know these all first, second, first, third, and fourth, they all include some kind of heat transfer. Okay, so some kind of heat evolution is there, and there will be, if there is heat, and we know heat is low grade energy, and if there is heat then there will be loss. Okay, and there is loss, then there is waste heat, so we can recover that. So in hydropower plant there is no combustion, there is no heat involved, there is direct mechanical work, because we are rotating turbine with the help of water. So there is, you can say, the kinetic energy is directly converted into, you can say, the force of water is rotating the wheel. So that kinetic energy the wheel is getting, so we can attach a generator to the that wheel, and we can convert the mechanical energy into electrical energy directly. So there is no heat involved. So there is the hydropower plant is not a source of waste heat, and fossil plant, as we know, that it's based on basically on combustion. We are using boilers, we are generating the steam, we are using the coal to generate the steam. Okay, in nuclear power plant also we are the reactions are like there is huge heat involved, and hot products also, like in metallurgical chemical industries, there is huge heat in reactions. Okay, so we cannot use that. So high amount of waste heat are available on these three sources. So the correct option will be option C, first, third, and fourth. So option C will be correct. Okay.
Sir, I have a small doubt, can I?
Yeah, please.
So as I said that renewable, okay, I have used a wrong term there, renewable source of energy. So it makes me curious to think, suppose if you are installing any solar power plant, and
Mhm.
in solar where the thermal energy interactions were there. And there also you can find, if you are finding any waste heat, are there any systems where waste heat recovery is being used? It's like, are there any such kind of things are implemented?
In practical, I don't aware of any system, or maybe there are, but I don't know.
Okay.
Yeah, I don't know. But if suppose if you are like if you're using solar thermal, then solar is you know solar is renewable, but still you are converting solar to thermal. Okay,
Mhm.
then there is a chance of waste heat recovery. So we can use that.
Okay. Okay. Thank you.
Yeah. So the main funda is that don't think that renewable source don't generate waste heat. It's not about the source. It's about the technology which we are using. Okay, because like conversion, like we are converting the energies. Okay, so think in that perspective. Like maybe your technology is that, because like you see, maybe either your process, either your technology is a reason for waste heat generation. Okay, so go through those points. It's not about the renewable source and all. The technology is also playing very important part in it. Okay, let's move to the next question. Question number 5 is, choose the correct statement regarding the forms of energy. So we are having different forms of energy. A is heat, work, and kinetic energy are forms of energy in transit. Only heat and work are forms of energy in transit. Heat, work, and kinetic energy are forms of stored energy. Only heat and work are forms of stored energy. Yeah, quite complicated. Okay, go through all the options.
Hello, sir.
Yeah, please.
Sir, the point B is right. Only heat and works are forms of energies, and all others are types of energies for a given, we can say, condition. For a given condition, what kind of energy that system, that body is possessing, whether it is type of kinetic energy, potential, maybe magnetic, maybe chemical. So all these they come, like they are types of energies what a body or a system is possessing at that given time. And only
Okay.
two basically forms of energies are there. Either it is heat energy or it is work energy. So that what we can use or we can convert to. Heat is converted
Okay.
to work and work is converted to heat. And remaining all, I think only point B is right.
So basically, what is the meaning of transient and store energy? Just differentiate it. Like it's saying that only heat and work are forms of energy in transit. So what is the meaning of energy in transit?
Sir, can I say, sir?
Yeah, please.
Sir, energy in transit means that the energy can be transferred beyond the boundaries of the system itself, sir. So, for example, only heat and work can be transferred between boundaries of a system, sir, whereas kinetic and potential can't really be transferred between the boundaries of a system, sir. It can only be within the system.
I don't
It's
think
like we
so.
can say it as, we can be saying as internal energy of the system. It's like kinetic
Yeah, you
energy,
can say
potential
the
energy, vibration
kinetic
energy.
energy. Suppose you are taking a system. Suppose I have a system like this. Okay. So maybe at this point and this point. So some part of fluid, mass flow rate m, okay, it will be having kinetic energy k1, potential energy p1 at point 1. At point 2, again same mass flow rate, K2, P2. Maybe this opening is slightly, we'll say it, narrow as compared to this. So do you think that the kinetic energy will be same on both ends, 1 and 2? What do you think?
No, sir. No.
No, sir.
No. But kinetic energy is coming now. You are saying that suppose this is the system. If my system is like this, system boundary is this. So you are saying that kinetic energy cannot be transferred through the systems. So yeah, it's transferring. The kinetic energy is coming, the kinetic energy is coming out. What do you want to say?
In transmit means they can be transferred, like heat energy can be transferred or can be converted into work, and simultaneously work can be converted or transferred in terms of heat energy. Like for example, kinetic energy, say for example, if I have potential energy kind of, and if I'm standing on a mountain, say much amount of potential I'm having. Now if I just slide down from the mountain, that is converted into kinetic energy. So it is not transferred. It will be the amount of potential energy, how much we are having, that is converted or that is equivalent, that is converted to kinetic energy. It is not transferred. So in case of heat and work, there is amount of heat energy which can be transferred. It's not possible to convert all heat energy, but on the contrary, we can convert all the work into heat energy.
You are on right path to answer, but you are not saying the exact thing, the meaning of energy in transient. You are correct, but you are just missing 1 or 2 words.
Okay.
Try to think more. Like you are saying that kinetic energy, so it's stored energy. Okay, what is the meaning of stored energy? Like suppose this point 1 is there. Okay, so suppose my condition is at 1. So at 1 I'm not moving. Okay, I'm still, my components, my gas streams is still at 1. So it will going to be have some potential energy, some kinetic energy. Okay, so is it having some work or some heat transfer at 1? What do you think? Only one position is there, location 1. Is it going to have some heat transfer or work transfer?
No, sir.
No, sir.
No, correct. Now suppose there is another location 2. Now my gas stream is going from 1 to 2. Now again at 1 there will be some kinetic energy, potential energy, and internal energy. At 2 also, because the gas molecules are moving everywhere and they are going having some temperature and all. So here also there will be kinetic energy, potential energy, and other stored in internal energy. Okay, so but this stream is going from 1 to 2. There is a process, there is a path. Now what else is here? What do you think? Anyone? What else energy now comes in picture? Now there are two systems, 1 and 2, they are interacting. Okay, now comes heat and work in picture. So the main point is that heat and work comes into picture only when there is a interaction. Okay, there is a path. Okay, there is a process, you can say. There is a in transition is there, like energy is transferring from one point to another point. Then only heat and work comes to picture. Otherwise, no. Otherwise, if we are only discussing about a still point, then there will be only stored energy. So that is the energy in transient. Okay, so we are like energy is moving from point 1 to point 2. So in this path, there will be heat transfer because there is ambient conditions are there. Okay, So maybe the energy, the stream is at maybe around 100 degrees centigrade, and the ambient condition is around 25 degrees centigrade. So there is a temperature difference. Whenever there is a temperature difference, there will be heat transfer. So there will be heat loss. Okay, maybe the environment is like hot. Environment is around 200 degrees centigrade, and the stream is 100 degrees centigrade. So this stream will take the heat from the environment. So there will be heat input. Okay, like this energy is going from 1 to 2. In between, you can place some motor and every like some mechanical part. Maybe that can rotate. Okay, so you can lift a weight. So maybe you can get a work from it. Okay, so you can. So think in that way. So these are the energy which comes into picture only when there is a transfer. Okay, so there is a transit. Transit means there is a way. We are transferring it. Okay, so heat and work only comes into picture when there is a transfer of energy. Otherwise, no. So that is the meaning of the energy in transient. I think I am clear.
Yes.
Is it okay?
Yes, sir.
Yeah. Okay. So the correct option will be option B. So only heat and work are forms of energy in transient. Choose the correct statements. The first one is heat and work are point function. All forms of energy in transit are point function and properties of a system. All stored forms of energy are point function and properties of a system. All stored forms of energy are path function and properties of a system. Go through all the points, and the answer is already we have discussed in our previous question. Try to remember that answer is in that only. Yeah, Wasim. Wasim, have you raised your hand? Yeah, please tell. I think one hand is raised, so you can ask your question. You can ask your question. Am I audible? Audible?
So answer is C.
Okay. Okay, no, nobody's asking question. Okay, maybe by mistake your hand is raised. Okay, no issue. So yeah, come to the question. So you are saying answer is C. All stored forms of energy are point function and properties of a system. Okay, let's wait for another 1 minute. Maybe anybody else want to answer or discuss? Anybody else want to add some point to this?
Sir, answer is C.
Okay, so yeah, answer is C. Okay, please explain your reasoning.
So because the energy, all stored energy is the point function. This is internal energy. So internal energy is the point function.
Okay.
And property of system. Because
Okay.
P and V and whatever is that is the property of the system.
Okay. So what do you meaning by the property of a system?
So property of system is that like the volume is the property of system, and pressure is the property of system, temperature is property of system.
So okay, these are the you have given the example. What is the like meaning of property of system?
So properties of systems are some characteristics of system that define the state. That, for example, properties of system can include volume, as my colleague said, volume, internal energy,
Yeah,
etc.
correct. So basically, it defines the state of the system. Okay, defined about a point or particular like what is the pressure, temperature. These are the properties. So it's defining the state. Okay.
Okay.
So that is a property. Now come to the point function. So what is the point and path function? What is the difference between point function and path function? Why, if you are saying the option C is correct, then you are saying the option A is wrong. So it means that heat and work are not point function. So if heat and work are not point function, so which function are they? Are they path function?
The path function, sir. Heat and
Yeah.
work is the path function because it's a depend upon the path under the area to get the work, and point function not depend upon the previous state. So the store energy is not depend upon the previous state. So,
Correct.
point function, store energy is a point.
Yeah, correct. So as we already discussed in our previous question, that heat and work comes into picture only when there is a process, or you can say there is a transfer between from state 1 to state 2. Okay. So, and that is also depend on the path, like by which path you are going to from point 1 to point 2. Okay. For a practical, like just for an example, we can say that there are multiple paths. So one path is having more resistance, one path having less resistance. You can think in that way. So there will be more loss in one path, less loss in other path. So in that way, so heat and work are path function, not point function. So option A is wrong. Option B. Option A is wrong. Option B, all forms of energy in transit are point function and properties of system. No, they are not point function because energy in transit are what? Work and heat
Is a
are
path
energy in
function.
transit, and they are path function. They are not point
And
function.
work is the transit.
Yeah. Option B is also wrong. Option C, all stored forms of energy are point function. Correct, because if you are having some temperature, pressure, okay, so these are all stored form because temperature may be due to the internal energy and all. So these are stored energy, and that will point function, and that will be also defining the system. So they are also property of a system. Option C seems correct. Option D, all stored forms of energy are path function. No, they are not path function. They are point function. So correct option is option C. Okay. Let's come to the question number 7. So consider the two statements for the first law of thermodynamics. We have given two statements, statement 1 and statement 2. Statement 1 is saying like that it's a cyclic integral delta Q is equals to cyclic integral del W. Del Q is equals to dE plus del W. So which of the following statements is or are correct? Go through all the options and also discuss your reasoning.
So option C is right here.
Option C. Okay, we will discuss. Just wait one more minute. Maybe some other will also try to answer.
I too believe so. Option C is correct, sir.
It is option C, sir.
So now we are having more answers, so we can discuss it. So let's start with the reasoning. Okay, the option A, I is applicable to for a single process. So why option A is wrong? The first statement is cyclic integral of delta Q
Because
is equals to cyclic
internal
integral delta
energy.
W. Yeah. Yeah, please.
Sir, equation 1 is the applicable cycle only.
Yeah, correct.
Because cycle
Because-
is the point.
And how do you know it's applicable to cycle only? How do you know?
Sir, may I?
In a cycle,
please.
starting from 1 point to come to again the 1 point, the internal energy is 0. U1 is equal to U2.
Yeah, that is fine. That is fine. But by seeing the equation 1, how can we say that it's only for cycle? Because its
So
cycle
you're
is
saying
not
it's
mentioned.
cyclic integral. It's like cyclic integral. You're telling.
Sorry?
We are while reading only we are saying that it's cyclic integral of heat is equal to cyclic integral of work.
Yeah, that's what I am asking. How do you know it's cyclic
So,
integral?
Simply say the cycling, no, sir.
Yeah, correct. That's what I am asking.
This
By the
symbol saying
symbol.
that cycle process.
Yeah. So what is the difference
This symbol
between
is
this
saying that cycle
integral
process.
and this integral? So there are two signs, sign 1 and sign 2. So in sign 2, there is a round at the center. Yeah, so this round is representing the cycle. Okay, circle is representing the cycle. So this sign is for cyclic integral. Okay, and the simple sign, it's for normal integral. So whenever you see this sign, it means that it's talking about cycle. So cyclic integral of delta Q is equals to cyclic integral of delta W. It's for a cycle. Yeah. Okay, now comes to the option B. Second is applicable for a single process. Yeah, please discuss your reasoning.
So may I?
Yeah, please.
So in second process, in second equation, when we do a thermodynamic process, that is a single process, the heat which we provide, it is divided into two parts. One changes the internal energy of the system, and second part of heat is converted into work.
Okay.
So we
This
can
equation-
simply say that heat and work interactions, what is the effect on to the energy of the system or the internal energy of the system.
So
Okay.
equation 2, this equation is saying there's a process.
Process. So
a process.
option B is correct or not?
B is correct.
Option B is correct because option 2 is for applicable for a single process. Okay. Now come to option C. I is applicable for a cycle and 2 is applicable for a single process.
C is right.
C is right. Okay. And option D, I and first and second both are applicable to a single process. It's wrong. So basically options B is correct and C is correct. Okay. But they have given only option C as correct because
So D is also correct.
no, option C, D is wrong. They have given that option C is correct only, but if option C is correct, it means that option B is also correct because 2 is applicable for a single process. So yeah, it's correct. Okay. So I think we have to clarify it because sometimes they have not mentioned that we have to okay. If we go through the options, so statement 2 is correct and C is both correct. So maybe we can raise a query to NPTEL team because I think both option B and C should be correct. Okay.
So can I add something to option 2?
Yeah, please.
So I think both answers are right, as you said. In case of 2, it is only possible if it is a process of heating. If I'm heating, say 1 kg of gas, I'm heating it. So initially, its internal energy will increase, and then parallelly there will be a change in its volume, and then work done. We can just obtain the work done in terms of change in volume. So that is very much possible in the process. Now the reverse is what in the cyclic process that is very much possible that the system will retain its initial conditions by giving out all the work is converted again back to the heat energy, or heat energy is converted into work. So I think both are right, because second one is only applicable for a process which is in a certain direction. It is not a reversible or not a cyclic process.
So maybe any one of you can, maybe I will raise a query and maybe you can also. So I think option B and C both should be correct. Okay, because if option C is correct, option B is automatically correct. Okay. So let's come to the next question. Question number 8. So which one of the following is steady flow energy equation for economizer shown in figure 1? Okay, you have to find out the steady flow energy equation. Consider flue gas duct wall is insulated. No work is extracted from any of the fluid stream and changes in kinetic and potential energies are neglected. Subscripts F and W are for flue gas and water respectively. Yeah. Take your time. Take 2 minutes. Find out the correct equation.
Sir, A is correct.
Oh, very fast. Okay, let's
I
wait for
think
one
it's
more.
wrong or right?
Maybe please wait a moment, 1 or 2 minutes. Maybe give some time to others to solve. So go through the diagram very carefully. Whenever you see this type of questions, it's just only for asking the equation, but maybe numerical maybe also come like this. So you have to check where is the inlet, where is the outlet, what is the flow rate, everything. Always write carefully, okay, with subscripts. Otherwise, maybe your equation is correct, but whenever you putting the values, maybe you do some mistake, typo error. Okay, so don't do these things. Otherwise, you don't get marks. So always write neat and clean. Try to highlight everything, like for what are the which like term is representing which value.
Sir, option B is correct.
Option B. Okay, now we have 2 options, so we have more to discuss. Okay, yeah. Anybody else?
Like, sir, can I give the reason in case for the option number 2?
Just wait a minute. Maybe option C can be also correct. Just let 1 more minute, then we will going to discuss it. Yeah, it's going to be
Option E.
okay. So we have 2 answers as option A, 1 answer as option B. Anybody else? Okay, let's start with option B. Okay, yeah, please present your reasoning.
Then here it is for steady flow case. There is work done. There is no work done. There is no work extracted here from any of the fluid, but there is an energy transfer in terms of heat energy. So there's hot fluid coming from one side and it is going out, and from the other hand, like we can see a simple heat exchanger, and in which there is heat energy extracted. The mass flow rate for both the cases of fluid at hot flue gases and water remains same at steady state condition, but there is some amount of heat energy which is transferred between them.
Okay, nice. Okay, nice. Now tell me just one thing. What is the equation 2? Like option B, it's saying that MF HFI minus HFE equals to MW HWE minus HWT plus Q. So what is this Q stand for? What is the meaning of this Q?
Q is earlier whatever the amount of like fluid which is coming, or the cold water, let us say cold water is entering, whatever the amount of energy it was earlier having, it will be having more now.
Yeah, actually, yeah.
Q is
Actually, yeah.
There's a rise in
Q is the
temperature
heat
of that.
transfer between system and surrounding.
Yeah, actually,
Because
you
here
have to.
no system and
Yeah. Okay. Let me complete it. Actually, you have to please again go through the notes. Okay. So Q is the like heat interaction. It will be from system to surrounding, either heat added or heat rejected, and W will be also the system to surrounding. So as we have given, the duct is insulated. Okay, so there is no interaction
transfer.
between, there is no heat transfer from system to surrounding. So this Q will be 0. No work is extracted. This W will be 0. Q will be 0. Okay. Only the fluid is exchanging the heat. Okay. Only fluid is coming out and coming and going. So this equation will be correct. So option A will be correct. In more detail, please go through the class notes because it's a very long derivation. Okay. You have to check what are the internal energy, everything, kinetic energy, potential energy, then enthalpy. Okay. So option A will be correct. Okay. There will be no heat interaction. There will be no work interaction because that is already given in the question. Duct wall is well insulated. No work is extracted. Okay. And changes in kinetic energy and potential energy are neglected. So the basic equation like this: M HI MI plus VI square by 2 plus GZ, okay, plus Q equals to M2, again H2 V2 plus GZ plus W. So W0, this Q0, this and this. And in detail, you can see the class notes. I think it's clear. So the correct option will be option A. Okay. Is the doubt clear about Q?
Yes.
No, it's clear. It's clear.
Yeah. Okay. Okay. Okay.
Enthalpy will remain same from inlet to outlet. There is no interest. There is no added or going out of the system.
Yes, right. Okay. Okay, thank you. Then come to the next question. Question number 9. So which of the following statements are true? We are having 4 statements. The first law of thermodynamics relates to the quantity of energy. Okay, we have to move a little bit faster because we have more questions and we have only half hour left. Okay, let's move a little bit faster. So which of the following statements are true? We have 4 statements. So anybody?
Sir, option C.
Option
C, sir.
Both of the above statements are correct. Okay, anybody want to discuss it? Quickly.
No,
Yes,
sir.
option.
Anybody wants to discuss, like give your reasoning?
No, sir.
No. We have to actually, reasoning is important. Yeah, don't be in hurry. Reasoning is important because if you don't discuss it, then it's not useful actually. Yeah, discussion is very important. So just tell me one thing. What is the meaning of quantity? Quantity of energy. The first statement is the first law of thermodynamics relates to the quantity of energy. Why the word quantity is coming here? What is the meaning of what is the significance of quantity?
It's like amount of energy being transferred on the.
Sorry, your voice was like very low.
It's like amount of energy. It's like what is the amount of heat being transferred into work and how much it is going as a form of internal energy, which states the first law of thermodynamics. But second law, you can have the at what temperature the energy is there, how much you can extract. So as you said that the temperature at 100 degrees centigrade, if you're extracting heat at 100 degrees centigrade, it's not useful. So such kind of things will be given by the second law of thermodynamics. So
Yeah, correct. So your quality, I am satisfied with your quality answer, but I'm again, please repeat about quantity. Just explain more about quantity.
The
So
quantity
it's
of
like
consumption of energy.
Yeah,
Basically.
yeah, correct. Conservation of energy. That is the right word. Yeah, actually, in the first law of thermodynamics, we are saying that we are transferring the energy. Okay, the complete energy will be transferred. Okay, there is no loss. So the quantity will remain same. The conservation of energy will be there in the first law of thermodynamics. And in the second law of thermodynamics, we are discussing about quality. We are discussing about irreversibilities. That the quality is important, like work, high grade energy. Okay, if we are having energy at 700 degree, that will be going to be more potential than the heat at 200 degrees centigrade. So quality is important. Okay. Anybody else want to add some points? Yeah, please.
So with respect to quality, there's a direction. Things like there is a particular direction in which energy will be flowing.
Yeah, that is also a good point. Yeah, because it's also relate about the direction. So we can go from the high energy to low energy. If you want to go from low to high, then we have to add some work here. So the correct option will be C. Both of the above statements are correct. Come to the question number 10. Which of the following is or are corollary of the second law of thermodynamics? Yeah, go through all the options quickly.
Sir, D.
Okay, let's just wait for 10-20 seconds more. Okay, let's start the discussion. Yeah, floor is open. Yeah, anybody start the discussion, please.
Sir, as we discussed in the before question also, it's like second law of thermodynamics which states the direction, higher energy state to lower energy state, concept of irreversibility where the
Direction is
losses will
there.
come into picture,
Correct.
disorderness will come, entropy,
Yeah.
where you can have this performance also we can measure using that second law of thermodynamics. And concept of temperature scale independent of material property is that it's like you can relate to T1 in that way. It's like
Actually, we can like the for ideal efficiency we can go for temperature.
Yeah, directly using the temperatures we can calculate the efficiencies directly.
Yeah. Okay. So yeah, basically option D will be correct. Correct option will be D. I think it's clear to everyone. Yeah. Okay. Let's move to the next question. So heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine the net power output. Hello, your voice was not clear. Please repeat. Hello. Yeah, please.
Sir, previous question, please come to previous question, sir.
Yeah.
Sir,
Your voice is not coming. Hello. I think you are having some issue in your voice. Please check your connection maybe. Am I audible? Yeah, now you are audible. Yeah, please.
yes, sir. The point number 5 is the concept of temperature scale independent of material. This is given.
Yeah.
The question is which is the following of the corollary of the second law of thermodynamics. Second law of thermodynamics says about the temperature of scale. It's a zero law of thermodynamics.
Concept of temperature in zeroth law. That is correct.
Thermodynamics, sir.
Yeah. But I think, yeah, we need to discuss it. I think I have to discuss it. Yeah. But in second law also we can, like, if we want to, like, if we want to calculate the, like, maximum Carnot efficiency and all, we are using the temperature. But you are saying correctly, because the origin is in zeroth law, temperature. Okay.
Sir, for absolute entropy, like if you want to define the absolute entropy, then the temperature scale is more important. So it is part of second law.
Yeah, because basically zeroth law is saying like that if temperature of if A are and B are in thermal equilibrium, B and C in thermal equilibrium, then A and C will also be in thermal equilibrium. So that is
It
like,
means thermal
yeah.
equilibrium.
Yeah,
Minus
that is
system.
about thermal equilibrium, right? Correct.
It's like equilibrium of states in that way. It's
States, yeah,
speaking.
that is not about the temperature scale. Yeah, it's in second law only, I think. Yeah, correct. So option 5 will be correct. Yeah. So, like, discussing about zeroth law, so a very good question comes to my mind always. I always try to ask to my students. So let me ask to you. There are two chairs, chair 1 and chair 2. Chair 1 is made of wood and chair 2 is made of iron. Okay, both are in open atmosphere. Okay, and the temperature of the atmosphere is around 55 degree. It's very hot out there. Okay, and you are alone and you have to sit on one of the chair. So tell me, like, on which chair you will sit, on chair 1 or chair 2? Both are in same atmosphere. The both conditions are same. The difference is that it's made of wood, it's made of iron. So on which chair you will sit and why?
So obviously it will be wooden chair, because the thermal conductivity of the wood is very less, so it will not absorb more heat. So the surface will be a bit cool compared to the iron one.
Okay, anybody else?
Sir, I would not be sitting on any of the chairs.
Okay, yeah. But suppose if you want to sit, then which chair you will choose?
So
At
would because the conduction heat conduct is a wood, sir.
Okay.
Heat conduction
So,
is conductivity
yeah.
is low in wood.
So suppose
Iron is high.
okay, the wood chair is having temperature T1 and the iron temperature is having temperature T2. So what do you think about temperature T1 and T2?
Correct. If it is a steady state for a given time period, then both the chairs will have the same temperature.
Okay,
Sir,
no. Don't go into steady state conditions. It's only in open environment. Don't go in depth.
Then T1 will be less than T2, sir.
Sorry. Your sound is not clear actually. The one is. I request you to please. I think please rejoin. Your sound is not coming correctly. Your sound is not coming correctly. Maybe you can check your internet connections.
I think it's Mr. Wasim. I think, sir, your audio is not at all proper.
Steady state where T1 is equal to T2. If not, it's
No. Actually, I mean, I hear question clearly. Don't go in steady state. Okay, we are not talking about steady state, dynamic, and all. Nothing. Just my very simple question. Suppose you don't know about steady state. There is open. There are two chair 1, chair 2. One is wood, one is iron. They are put. They are in open atmosphere. The temperature is 55 degree of the atmosphere. Okay, so the chair 1 is having temperature T1, chair 2 temperature T2. So what about the temperature T1 and T2? Will they equal? Will T1 is greater than T2 or T2 is greater than T1? Yeah, now please tell me one by one.
T2 will be greater than T1, sir.
Okay, so what's your name? You saying T2 will be greater than T1. Okay. Second, anyone else? Anyone else,
So-
please?
If I'm not wrong, T1 and T2 are the temperatures of the chairs, right?
Yeah. T1 temperature of chair 1, T2 temperature of chair 2, made of iron. Chair 1 is made of wood.
Yes, sir. Then I'll also go with the first option. T2 is greater than T1.
T2 is greater than T1. Okay. What about anyone else? Wasim, Mr. Wasim, are you there? I think your audio is now maybe clear. Please share your thoughts.
I think Wasim is not available.
He's not there.
We will rejoin
Okay.
him.
Maybe he's checking his connection. Okay. Anybody else want to answer? I think the guy who were discussing about zeroth law. Have you answered the question?
Yes, sir. I think sir, T2 will be greater than T1.
Okay. So everyone is thinking that T2 will be greater than T1. That's why you are sitting on wood chair. Am I correct?
But I have a
Yes.
question that what are the temperatures of chairs before you are placing into the environment, in that environment?
No. I am saying that they are putting outside. They are like putting from like maybe 5 or 10 hours.
It's like simply they are in normal condition chairs only they are keeping. It's not like some iron. So it's like suppose you are keeping a chair of 70 degrees centigrade of iron chair into the 55 degrees centigrade means.
No.
That
Both chair initially were at room temperature. Then they were
okay, so
in
then
this
it's fine.
temperature. They are there for a
Then
long
it's
time. Now think about the answer. So you think T2 is greater than T1. Okay. So I think
Yes.
okay. So I
Yes,
think
sir.
one of you will telling about some thermal conductivity.
That's what coming into the picture. If I say that iron might cool faster than the, in that case also it can happen.
Yeah. That is actually, you know the answer, but you're thinking like you are not thinking fundamentally. So the correct answer will be T1 equals to T2. Both chair will be at equal temperature. Here comes the zeroth law. Because the environment is 55 degree, chair 1, chair 2, both are on the same environment. So they will be in the thermal equilibrium with the environment. So both chair will be 55 degree, but you feel cooler at wooden chair because of the thermal conductivity. Okay. But the temperature of wooden chair is also 55 degree. Because thermal conductivity comes into picture when there is heat transfer. Okay. So suppose when you sit on the wood chair, so the immediate wood particle will transfer heat to your body, and your body is very large. So you don't feel any heat because the next particle, suppose this is your body, okay, and these are the particles of wooden chair, small particles. So one particle transfer heat to your body, and the next part is also 55 degree, but the conductivity is very less. So that particle will take time to transfer the heat to this particle. Okay, in this
You're
way.
telling that the rate of heat transfer in the iron chair is greater than the rate of heat transfer in the wood. That's why you're feeling the immediate effect.
Yeah, right. Because iron chair, the conductivity is higher. So rate of heat transfer will be higher. Okay, so you know the answer, but you are interpreting it wrong actually. The both temperature will be same. It's only about feeling. Okay, because it's only about the heat transfer, the transient heat. I think doubt is clear. So the correct answer will be T1 equals to T2. Is it clear to everyone?
Sir, like if we keep these two chairs in the morning and let
Okay.
us till afternoon we are keeping it in the outside, the condition of outside are same throughout from morning to afternoon. It is 55 degrees only. So
Yeah.
like what generally like At afternoon, can we know that the temperature will be same?
Yeah, same. Yeah. Because maybe if you are only taking afternoon, maybe the iron will be slightly more. But I am saying, but you have to go through my question. I am saying na, they are putting. I have not mentioned like 2 hours, 3 hours, because it will apply to both. Because if the
So you are
wood
not
chair,
talking about the rate of heat transfer, but you're talking about the equilibrium state.
yeah. No, I am talking about both. The chair are. I have mentioned that chair for a long time. So long time means they are in equilibrium. And rate of heat transfer will come into picture when you sit on them. That's why when you
Yes.
feel temperature, I'm asking about T1 and T2. When you sit on the chair, so you will feel that T2 will be more heated than T1, but in actual, no. Both are at same temperature. It's just only heat transfer. In T2 chair, in iron chair, you will feel like heated because there is high rate of heat transfer there from chair to your body. So your body will feel more heat. Okay, and in on the wooden side, the conductivity is very low. So the heat transfer rate will be very low. So you feel that this chair is little bit at lower temperature, but that is not correct. Temperature will be 55 degree only. That is the question. Because the particle of chair of wood particle, the wooden particle will be quickly come to a very lower temperature after your contact with the body. Okay.
So, that means this complete whatever the model we are talking about, this is under the steady conditions, right? Like as I earlier said, like at steady conditions, like I said, I will not be sitting on both the chairs because at steady conditions, both the chairs will have the same temperature. So that's
No, steady condition, yeah, it's fine, but we don't have to mention that because you have to understand it actually.
Yes, sir.
Because
yes, sir. I got
yeah, you have to understand it now. Because if I'm saying the steady state, then you directly say, but you have to learn the concept actually now. If they are, I'm saying that they are for a very long time, they are so the main point you to understand the temperature equilibrium, the zeroth law of thermodynamics. That is the main point. Don't go into steady state.
Yes, sir. Yes.
Okay, steady state will come into picture when we are talking about like something is moving, and we are now talking about like particular states only. Okay, but they are already there. Like there is nothing you can say that air is moving, but don't go into that depth. We have to just only go up to zeroth law of thermodynamics.
Yes, the temperature will remain same. They are in thermal
Yeah.
equilibrium with each other.
Yeah, that is the concept. Yeah, because temperature will be same. So T2 equals to T1. That is the main point. That is the actual zeroth law of thermodynamics. Because both are in open atmosphere, so they will come into the equilibrium with the atmosphere. It's only about the feeling. It's only about the rate of heat transfer.
Yes, sir. It's a very good example, sir. Actually. Yes.
Yeah. Because every time, actually, whenever the zeroth law comes, I ask this question, and most of time everyone will get confused. Okay, come to the question number 11. Heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine the net power output and thermal efficiency of the heat engine quickly. Please try to answer it.
Sir, output is 80 minus 50 is 30, and 50 divided by 30, 50 divided by 80, you get the efficiency.
Yeah, actually, you have to give me the answer. I'm not going to use the calculator. Actually, yeah, you have to use it.
Sure, we can find out the work output. And
What is the answer?
37.5%, sir. 37.5% efficiency.
37 point. Okay, we have one answer. Anybody else wants to add answer? Then please quickly. Okay. So the answer will be option C, 37.5. So here you can see we are having a furnace at temperature T1, river temperature T2. Okay, so T1 is greater than T2. So some heat transfer is there, heat engine is there, it developing the work. Okay, so the W will be Q1 minus Q2. So 30 megawatt will be the work. Now the efficiency is output upon input. So net rate of work output is W, input is heat Q1. So W upon Q1, 30 upon 80, it comes to 0.375. But we have to give the answer in percentage. Okay, so don't confuse with option B. Okay, it's in percent. So we have to multiply it with 100. So it's going to be 37.5. So correct option will be option C. Is it clear?
Sir, in question asking two things, sir. Determine the net output and thermal efficiency. Given option only was
Yeah. There are two options. They are asking two, but only option is only for efficiency. Yeah. So you have to check the options only. Yeah. The power because if you don't know the power output, you cannot calculate the efficiency. So the question is smart actually, because after the power output you can only know the efficiency.
That's why they have mentioned determine the net output and then find out the efficiency.
Right. Okay. So I think it's clear to everyone. Okay. Let's come to next question. So a heat pump is used to meet the heating requirement of a house and maintain it at 20 degree on a day when the outdoor air temperature drops to -2 degrees centigrade. The house is estimated to lose heat at a rate of 79200 kilojoule per hour. If the heat pump under these conditions has a COP of 2.5, the power consumed by the heat pump is a very big question. Yeah, please start the solution. You have 2 minutes. Please be careful with the signs actually. Yeah, it's -2 degree. Be careful it. So you have given a COP, so you have to know the formula of COP, coefficient of performance, apply that formula. You have the value, yeah, you will know the answer then. So one a very easy trick to this type of question, always try to draw the diagram first. Okay, don't go directly with the formula, maybe you get confused. So always try to
8.8.
Yeah, 8
Option
point.
B. Option B.
Okay, we will see it. So always a quick tip is that always try to draw a simple a schematic, okay, in which you can see the heat engine, reservoir, and source, and Q1, and always mention the Q1, Q2, W, and everything. Then only start the applying formula. Then you will never get the wrong answer. Yeah. So the correct option will be 8.8. So it's B. So you can see here a basic simple diagram. It's representing house, outdoor -2 degree, house 20 degree. There is QH, there is QL, L low temperature, high temperature, W is work done. Okay. So we have given the heat. So we know the COP is heat pump is the QH upon work done W. So we know we have given the COP. So just interchange the quantity. So W will be QH upon COP. We have QH. Okay, COP, okay, it's kilowatt hour. So point to be noted here, it's in kilojoule per hour. Kilojoule per hour. But for watt, we need joule per second. So you have to convert R to second. Okay, so remember that. Then only you will get the right answer. It will be 8.8 kilowatt. You can do the calculation. Is it clear? always try to remember the units actually. Yeah. Whenever you are calculating, just a tip, maybe you are all aware of it, but I have to repeat it. Always try to remember the units, like in watt unit, the answer is asked, like maybe it is written in kilowatt, maybe it was written in watts. Okay. So try to remember the unit in which answer is asked, and always see the units in which the quantities are given. So here we have again kilojoule per hour. So you have to change it. Try to remember these things. These are very minor things, but these are the main reason for wrong answers. Again, question number 13. What will be the efficiency of a heat engine operating reversibly between the temperature limits T1 and T2, where T1 is the temperature of the source and T2 is the temperature of the sink, as shown in figure 2. Yeah, please quickly.
%14.27%, option C.
Option C. Okay. Okay, let's see the answer. Yeah, it's 14.27%. So we have to apply the basic formula. Carnot efficiency T1 minus T2 upon T1, or you can say 1 minus T2 upon T1. So
Sir, I add one point here.
yeah,
So
please,
as we
please.
discussed in earlier question, how that the second law of thermodynamics, the Kelvin scale is related here. So it's like if you don't convert the values into Kelvin, you will get a wrong answer again there. That's how the second law of thermodynamics is related in this equation. It's like independent of the material property. So you have to convert into the Kelvin compulsory.
Yeah. It's a very good point. Yeah, it's a very good point. Yeah, thank you. So yeah, you can see you have to always convert temperature into Kelvin only. So that's how the second law is connected to the Kelvin scale, temperature scale. Okay. So you have to convert it to the Kelvin, and then only you will get the right answer. So its right answer will be 14.27. Question number 14. Choose the correct statement. COP of heat pump, COP of refrigerator, COP of heat pump. We have given some COPs. See the diagram, figure 3, and mark the correct answer. Yeah, please.
Option D, sir.
Option D.
Option D. Yeah.
Option D,
D,
sir.
D. Option D,
Correct.
D.
Yeah, option D. The correct option will be option D, because we know that COP of heat pump is 1 plus COP of refrigerator. Okay, for refrigerator we have to take COP of Q1. Okay, heat pump is COP of heat pump.
Like
Yeah, actually.
By work input. Desired effect by work input.
Yeah, actually. Yeah, here should be, I think, for heat pump, desired effect will be Q1.
Q2.
So it should be, sorry?
Desired effect will be Q2 now. So it's like you are heating the system there. So you're pulling the heat from Q1.
Okay. Yeah. Arrow is this side. Yeah, arrow is this side. Okay. Its actual screen is very small. Okay, yeah, arrow is this side. Yeah, see the arrows. Now, for HP, it's Q2. For refrigerator, it will be Q1. Okay, now all options are correct. Yeah, actually, in my screen, it was like arrow like this side, I thought. Okay, so arrow is like this. So now the lower temperature will be effect of refrigeration. The higher temperature will be effect of heat pump. Okay, so you can relate that. So question number 15. A heat engine operates between a source temperature and a sink temperature. Okay, what will be the least rate of heat rejection? Yeah, point to be noted. Least rate of heat rejection. Now apply the formulas. Yeah, please tell me the answer. A small trick is there, least temperature. Please focus in this. Anybody? Anybody got the answer? Okay. So we have given that the least
210.
rate of heat rejection.
210.
Okay, 210. Yeah, correct. So the correct answer is 210. So the main point in this question is that least rate. So whenever, so when will you get the least rate? Whenever you are having the highest efficiency, mean Carnot efficiency, then
Carnot
only
efficiency.
there will be least rate of heat rejection. So just apply the formula of Carnot efficiency. Just draw a simple diagram. Okay, apply the Carnot formula, n max 1 minus T2 upon T1, you will get 0.7. So this will be the maximum efficiency. So now W net upon Q1 equals to n max. Now you know the Q1. Okay, you know the W net, so will be 490 kilojoule. You know the Q1, so Q2 will be Q1 minus W, 210 kilojoule. Okay, it's quite simple. But the main thing is that you have to know what is the least rate of heat rejection, when it will be applicable. So it will be applicable only when there will be the maximum efficiency, and maximum efficiency will means Carnot efficiency. I think it's clear to you.
Yes, sir.
Yeah. So I think our 5:30 is in my 5:30 your 9 p.m. actually. Yeah. So I think our time is completed. So I think it was a very good session. Yeah. Actually, I enjoyed it. Yeah. So because you were participating, it's a very good things to discuss things. So any feedback like how we can more improve it? Please share your feedback.
Sir, I want to share one thing, sir. It's Varun Kumar. Okay, I work in a consultant company.
Okay.
So after it's like almost after 2 years, I'm doing such kind of conceptual things. It's like every day we'll be running for the deliverables. So we'll be
Yeah.
not talking about fundamentals. It's like hectic thing. We were not able to sit for 1 hour in a meeting, but for still
Yeah.
it's like 2 hours. Literally, I'm enjoying the session like anything. It's like
Oh,
I'm going
nice.
back to
Yeah.
my
Thank you.
days again. I should really thank this platform for this. Why? Because I know as I am working in that consultancy field where we run for the business only mainly,
Yeah.
rather than
Right.
optimization or innovations, mainly for these kind of things. So this is kind of like refreshing again for me. As I should thank you for this.
Yeah. Thank you. So I hope you will always join 7 to 9 every Monday. Sorry,
Sure,
every
sure.
Friday. Yeah. Yeah.
Yeah,
Yeah.
it's like a refreshment for me from these kind of things.
Yeah. It is very good for me also because if the audience is interacting, then it's going to be very fun actually. Yeah. the reading and the studying is in a fun way. It's a very good thing. Yeah, we can discuss it. Yeah, and we can get more opinions, more thoughts about everyone. Yeah, it's good actually. Yeah. Anyone else want to give any feedback, like how we can further improve it, or any suggestion? Anyone? Okay. So okay. So I will share the recording with you. I will share the PPT. In this PPT, there are more questions. Yeah, please.
सर आप every Friday class लोगे या
This
कोई और
class
representative?
will be every Friday 7 to 9. 7 to 9
सिर्फ
I
आप ही
will be
लोगे या
here.
कोई और भी?
No, 7 to 9 I will be here. Every Friday 7 to 9 I will be here. Maybe कुछ और TA भी होंगे. Some more TAs are there, but they are having some other days. But every TA will discuss the same week course. Okay.
Okay, sir.
The other TA also will discuss the week one class lectures, but maybe timing will be different. But every Friday 7 to 9 p.m. I will be here. Maybe if some emergency is there, then I will
For this
reschedule
subject
it.
only.
Yeah,
For this subject,
only.
no, sir.
For this subject.
Okay, sir.
Yeah. Like for today's class for week 1, so next class will be next Friday for week 2. So I always suggest before this class, I suggest that you go through the class videos or maybe class notes, because that will be very beneficial to you. Because if you are aware about the basic concept that were taught in the class, then you are going to have fun in the problem solving session. Because if you are solving the problems, then if you are interacting it, you are taking part in the discussion, then it's going to be very useful. So if you know, if you have gone through the classes, then only you will interact it. Yeah. So try to go through the videos. Maybe that will be very useful. And next Friday again we will discuss like these questions. So in this slide, actually I put 31 slides. More questions are there. So but due to the time limitation, you can try at your home. Okay. And we will maybe discuss in next class also if we have time. And you can also put an email. Okay. So there is a course discussion form. So you can put your doubts on that forum, and we are happy to answer. Yeah.
Sir, if possible, some few additional questions at the end of the every session during Fridays.
Sorry. Pardon?
Give some more
Like
questions.
he was telling that you can put more and more questions as possible so that we can work out in the weekends. It's like that's what he was
Yeah.
telling.
Actually, yeah, questions are there. Yeah, you can. I think 15 questions are more questions are there, so you can try these questions. No issue. And you can. I think the professor has also mentioned some reference books at the starting of the slides. You can also refer some books also. Yeah, but I will try to add more questions in every slide every week, as your maybe to try at your home. Yeah, no issue. Okay, then I am ending my slideshow. Okay. So, okay, thank you for joining. Okay, it was a great time with you all. So I hope everyone will join next week also. So I hope to meet you. Okay. Okay, thank you. Thank you, everyone.
Thank
Bye-bye.
you, sir. Thank you very much.
Bye-bye.
Yeah. Bye.
Thank you.